In this episode, we are stepping into a part of cybersecurity that feels very different from ordinary office networks because the systems involved do not just support email, files, and business applications. They may help run electricity, water treatment, pipelines, manufacturing lines, transportation systems, or other services that people depend on every day, often without realizing how much software and networking sit behind those physical processes. When security professionals talk about scanning critical infrastructure systems, they are talking about environments where digital weaknesses can affect physical operations, which means the stakes are often higher and the room for error is smaller. The title includes operational technology, OT, industrial control systems, ICS, and supervisory control and data acquisition, SCADA, and all three terms point to technology used to monitor, control, or support physical equipment and industrial processes. For a beginner, the most important starting idea is that scanning in these environments is not just a security task in the ordinary sense. It is a careful balance between learning where weaknesses exist and avoiding actions that could interrupt, destabilize, or endanger the systems that keep essential services running. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A good place to begin is by understanding why these environments are treated differently from traditional information technology systems. In a normal business network, security teams usually care a great deal about confidentiality, integrity, and availability, but in critical infrastructure environments, availability and safety often dominate every conversation. If a file server slows down for a few minutes during a scan, that may be inconvenient, but if a controller that helps regulate pressure, temperature, flow, or timing behaves unexpectedly, the impact could be far more serious. That is why defenders in these environments cannot assume that common scanning habits from standard enterprise networks will automatically be safe or appropriate. Many devices were designed years ago with reliability and long-term operation in mind, not with modern security testing in mind, and they may react poorly to unexpected traffic or aggressive inspection. Once you understand that difference, the entire subject becomes easier to follow because the goal is no longer simply to find everything as quickly as possible. The goal is to improve security while preserving stable operations and protecting the physical process that the technology exists to support. Critical infrastructure systems often contain a mix of modern and legacy technology, and that mix creates part of the scanning challenge. Some assets may be newer servers or workstations that resemble ordinary business systems, while others may be specialized controllers, sensors, human-machine interfaces, engineering workstations, data historians, or network appliances designed for very specific operational tasks. Certain devices may run old operating systems, use vendor-customized software, or rely on industrial protocols that were never designed with strong security controls in mind. Many of them stay in service for years or even decades because replacing them is expensive, disruptive, and sometimes operationally risky. That long lifespan means security teams often inherit fragile environments where patching is slow, vendor support is narrow, and change management is tightly controlled. For a new analyst, this is important because it explains why a scanning decision in OT, ICS, or SCADA is rarely just about technical capability. It is tied to asset age, vendor constraints, operational criticality, safety concerns, and the reality that some systems cannot be touched casually without serious review. Before scanning even becomes the focus, defenders first need to understand what they are dealing with. Asset inventory matters everywhere in cybersecurity, but it becomes especially important in critical infrastructure because organizations sometimes have incomplete visibility into what is actually deployed, where it is located, and how each component affects the physical process. If you do not know which devices control safety functions, which ones only support reporting, which ones are directly involved in process control, and which ones bridge between industrial and corporate networks, then scanning decisions become much more dangerous. A server in a support role might tolerate deeper inspection than a controller managing real-time operations, but you can only make that distinction if the environment, is mapped well. Analysts therefore need to think beyond simple asset counting and instead understand asset function, communication patterns, ownership, maintenance windows, and dependencies. In these environments, scanning without context is a poor habit because the same technique that is harmless on one asset may be unacceptable on another, even when both assets appear to be part of the same industrial site. Another major difference in critical infrastructure is that visibility must often be gained gradually and deliberately. Security teams frequently begin with passive methods because simply listening to network traffic or observing existing communications is safer than sending large amounts of new traffic into a fragile environment. Passive observation can help identify devices, protocols, software characteristics, and relationships between systems without forcing those systems to respond to a direct scan. That does not make passive methods perfect, because they only reveal what is actually visible in the traffic being observed, but they often provide a safer first layer of understanding. Once analysts build confidence in what the environment contains and how the devices behave, they can make more informed choices about where limited active scanning might be acceptable. For beginners, the key lesson is that in critical infrastructure environments, the scanning strategy is usually shaped by caution first and completeness second. This does not mean defenders accept blind spots forever, but it does mean they earn visibility in stages rather than treating the network like an ordinary collection of office endpoints. Active scanning is still relevant in many industrial settings, but it must be approached with far more discipline than people often expect when they first learn vulnerability management. Sending traffic to discover open services, identify versions, or test responses can provide valuable information. Yet the same activity may also create unexpected load, trigger faults, confuse legacy devices, or interrupt communications in systems that were not built to handle frequent probing. That is why active scanning decisions often involve detailed coordination with operations teams, engineers, vendors, and site owners before anything is run. The question is not merely whether the scan can collect useful data. The real question is whether the value of that data outweighs the chance of affecting stability, availability, or safety in the operational process. Some environments allow only tightly scoped active scanning against specific support systems, while others may permit broader assessment during carefully planned maintenance windows. A thoughtful analyst learns that in critical infrastructure, restraint is not a weakness or a sign of poor security maturity. It is often a sign that the organization understands the consequences of careless testing. The protocols used in industrial environments also change the scanning picture. Many business networks rely on protocols and services that security tools have studied for years, but industrial networks may use specialized communication methods that carry process information, device instructions, or telemetry between controllers and supervisory systems. Some of these protocols were designed more for reliability and operational function than for security, which means they may expose useful information to defenders while also behaving unpredictably under aggressive inspection. A scanner that works well against common enterprise services may generate confusing or unsafe outcomes when pointed at industrial communications it does not fully understand. This is one reason generic scanning approaches can be risky in OT, ICS, and SCADA environments. Analysts need to know not only that a device is present, but also what kind of role it plays, which protocol families it depends on, and whether those protocols can tolerate the sort of interaction that a typical vulnerability scan creates. In practice, protocol awareness is part of environmental awareness, and both are necessary before any responsible scanning plan can be developed. Vendor guidance matters much more in these environments than many new analysts initially assume. In an enterprise setting, security teams often feel comfortable scanning general-purpose systems on their own authority, especially when those systems are well understood and broadly supported. In critical infrastructure, however, some devices come with strict vendor recommendations about testing, scanning limits, approved methods, maintenance procedures, and support implications. If a site ignores those constraints and a device malfunctions, recovery may be difficult, slow, and expensive, and the vendor may not respond favorably if the issue resulted from unauthorized testing practices. This is not simply a legal or contractual detail. It is part of operational risk management because the organization may depend heavily on vendor expertise to troubleshoot or restore specialized equipment. Good analysts therefore treat vendor documentation, engineering guidance, and support agreements as part of the security context rather than as annoying external obstacles. Protecting critical infrastructure often means understanding that the technology is embedded in a much larger ecosystem of maintenance models, operational procedures, and business relationships that influence what safe scanning really looks like. A beginner also needs to understand that vulnerability findings in industrial environments do not automatically mean the same thing they would mean in a normal office network. In traditional systems, a missing patch or weak service may quickly lead to a routine remediation cycle, but in critical infrastructure, the path from finding to fix is often more complicated. The asset may be tied to certification requirements, production schedules, safety controls, or vendor-approved upgrade paths that limit when changes can happen. There may be compensating controls such as segmentation, restricted access, monitoring, or physical security that reduce immediate exposure even if the technical weakness remains. This does not mean the organization should ignore vulnerabilities, but it does mean analysts must interpret them in context rather than assuming every finding demands the same response speed and method. Security in these environments is less about blindly pursuing theoretical perfection and more about reducing practical risk without undermining the mission of the system. That mindset is essential because defenders are balancing cyber risk against operational risk, and in critical infrastructure, both forms of risk can have serious consequences. Network architecture plays a large role in how scanning is performed and how findings are interpreted. Many industrial environments are designed with layers, zones, or boundaries that separate business networks from supervisory systems, control networks, safety functions, and external access paths. Those boundaries matter because they influence both exposure and acceptable assessment methods. A support server located near the enterprise side of the environment may be scanned more like an ordinary server, while a controller deep in the process network may require passive observation, a vendor-approved method, or a maintenance window review rather than direct probing. Analysts therefore cannot treat the environment as flat, even if it appears connected on paper. They must understand which segments are more sensitive, which assets are exposed across trust boundaries, and where the highest risk communication paths exist. Once again, this reinforces a major lesson of critical infrastructure security. The technical act of scanning is inseparable from environmental context. You are not only asking what a scanner can do, you are asking where it is doing it, how close the target is to the physical process, and what kind of disruption would matter most. Change management is another crucial concept because scanning in these environments is often as much an operational event as a security event. In many industrial organizations, changes to systems are tightly controlled, scheduled, documented, and reviewed because even minor disruptions can affect production, service delivery, or safety conditions. A vulnerability scan may feel simple from a cybersecurity perspective, but to an operations team it may represent unplanned traffic, uncertain device behavior, and the possibility of downtime. That is why mature organizations treat industrial scanning as a coordinated activity that may require approvals, testing plans, fallback procedures, staffing support, and communication with multiple stakeholders before the work begins. Beginners sometimes interpret this as bureaucracy, yet in reality it is part of respecting the mission-critical nature of the environment. A well-run change process reduces surprises, creates accountability, and helps ensure that security work supports rather than conflicts with operational priorities. In a setting where real-world services depend on stable performance, that discipline is not excessive. It is part of what responsible defense looks like. One of the most valuable habits a new analyst can develop is learning to think in terms of consequence rather than just technical severity. A vulnerability that seems severe in a report may carry very different practical risk depending on whether the affected device is isolated, monitored, difficult to reach, or backed by safety controls that reduce the chance of real exploitation. At the same time, a weakness that looks modest in a generic scoring model may deserve urgent attention if it sits on a communication path that could affect a critical process, a public utility, or a system tied directly to health and safety. This is especially important in OT, ICS, and SCADA environments because business impact can include operational interruption, equipment damage, environmental effects, or public service disruption rather than just data loss. As a result, scanning is only useful if the findings are translated into meaningful risk understanding. Defenders must ask what the asset does, how reachable it is, what would happen if it failed or was manipulated, and how realistic exploitation would be under the actual conditions of the site. The human side of the work matters just as much as the technical side. Security teams cannot scan critical infrastructure effectively if they treat engineers, operators, maintenance teams, and site leaders as obstacles rather than partners. Those people often understand the process better than anyone else, including which devices are fragile, which systems can be touched safely, and which operational moments are most sensitive. Their knowledge helps security analysts avoid naive decisions and build assessment plans that produce useful security insight without harming the environment. In return, analysts bring visibility into weaknesses, exposure paths, and threat considerations that operations teams may not be tracking closely. The strongest outcomes happen when both sides respect what the other knows and work toward a shared goal of keeping essential services safe, reliable, and resilient. For beginners, this is a powerful reminder that industrial cybersecurity is deeply interdisciplinary. Success does not come from the scanner alone. It comes from combining security thinking with engineering awareness, operational discipline, and clear communication across the people responsible for the system. Over time, organizations that handle critical infrastructure well tend to move toward a layered approach. They build asset visibility carefully, use passive methods where appropriate, scope active methods cautiously, respect vendor and operational constraints, segment networks thoughtfully, and interpret vulnerabilities in terms of process impact rather than raw technical output alone. They also recognize that not every weakness can be fixed immediately, so they lean on compensating controls, monitoring, access restrictions, and prioritized remediation strategies to reduce risk without destabilizing the environment. This kind of maturity is important because critical infrastructure security is not a one-time cleanup project. It is an ongoing process of understanding a living environment that includes old systems, specialized devices, long asset life cycles, and high-consequence operations. Once you see the subject that way, scanning becomes just one part of a broader effort to create safe and resilient operational systems. That broader view helps analysts stay grounded, because it keeps the purpose of vulnerability work tied to mission protection rather than to report generation alone. The central lesson is that scanning critical infrastructure systems requires a different mindset from scanning ordinary information technology environments. In OT, ICS, and SCADA settings, defenders must care not only about discovering vulnerabilities, but also about preserving availability, protecting safety, respecting operational dependencies, and understanding the physical consequences that digital actions can trigger. Passive observation, carefully scoped active assessment, strong asset awareness, vendor guidance, architecture knowledge, and close coordination with operations all play a role in making that work responsible and effective. A scanner by itself does not make an environment secure, and in the wrong hands or used in the wrong way, it can even create new risk in places where stability matters most. When you understand that balance clearly, you begin to think like a real analyst in high-consequence environments. Someone who recognizes that the purpose of scanning is not to prove how aggressive a security team can be. It is to reduce risk intelligently while protecting the essential services and physical processes that people rely on every day.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.